Welcome back. This is Samaya Madhavan, and you're watching the series on convolutional neural networks. This is the third part in the series, and today we'll be talking about convolutions.
So far in our previous video, we discussed what image channels are. We looked at how any image can be represented in its pixel format, and for a color image, these pixels would be represented along its green, blue, and red channel. Next, we'll look at what convolutions are and how convolutions help us to effectively represent the information that's represented in these pixels. Now that the image has been represented as a combination of numbers, the next process is to identify key features within the image. This is extracted using a method called as convolution. So convolution is an operation where one function modifies the shape of another function. So convolutions in images are usually applied to either sharpen an image, smoothen an image, or maybe like intensify an image. But within like CNN, convolutions are applied to extract most prominent features within these images. So for the sake of understanding, I'm going to show you guys how convolutions work with just the blue scale on my screen. But in a futuristic slide, I'm also going to show you guys how it's typically applied to all the channels, which is the red, green, and blue channel. So how are these features detected? So to do that, we use a filter or a kernel that's represented by an, in this case, a 3x3 matrix, but it's generally an n cross n matrix. So this is what we call as a filter, or it's also called as a kernel. And this is your blue channel pixel representation of your image. So this is essentially your input image, right? Make it look better. So that's it. How do we extract it? So we take this 3x3 matrix, which is the filter in this case, and then we run it through every 3x3 matrix in our input image. So to just let the animations roll in, you see that the filters are just multiplied with each of these cells, corresponding cells, and then we take an addition of it. So to show you guys an example, so we multiply 60 times 1, which is this element, multiplied by its corresponding 0 cross 0, plus then we do 165 plus times 1 plus 187 times 1, which was 165 times 1, and 187 times 1, which is what I've represented over here. And then you move on to the next column, and then you multiply 7 times 0, 159 times 0, and 204 times 0, right? So I'm going to write that now. 7 times 0 plus 159 times 0 plus 205 times 0. Now we'll move on to add the next column with minus ones, which would be 98 times minus 1, 147 times minus 1, 165 times minus 1. So that would be 98 times minus 1 plus 147 times minus 1 plus 165 times minus 1. And then when you add all of these zeros are going to cancel out. So it's essentially the sum of these three numbers subtracted by the sum of these three numbers, because you're multiplying it by minus 1. And then you can do the math and you'll see that it's come down to 2. So what happens after that? So like you saw in the graphics again, this 3x3 matrix is going to, it started with the 0th column, and then it went up to the second column, and then in the next pass it will start with the first column and then go until the third column if it's 0 based. And then that's how you derive this value over here. And then the next pass, it will start from one column further down until the last column. So that's 3 column. Uh, so it's all still going to be until this row, right? And then that's how you derive 1, 1, 1. And I encourage you guys to do the math behind it to validate that these numbers are right. And then after you finish populating the first row over here, we roll this filter down by 1 row. So now again, this filter is multiplied by starting with the second row until the third, fourth row over here. And then so the first pass would be this over here until here. And then that's how you populate 48. Next you would like move on to the next column, populate 133 and 30, and then you get the idea. Now we would roll down to another column, another row over here, and then keep populating the final rows over here. That's how your your output, or this output over here is called the feature map. That was the name that I was looking for. Perfect. So that's how you derive the feature map. So how is the size of the feature map determined? It's a combination of your input image and the size of your kernel. So for an n cross n image, which is 5 cross 5, and m cross n filter, which is 3 cross 3, the resulting output is n minus m, so 5 minus 3 plus 1 times 5 minus 3 plus 1. The result is 3 cross 3. It just so happened that the feature map over here is of the same size as the filter, but it's usually not necessarily the same size. It's a combination of your input size and your filter. And so how are filters determined? So the filter that you see over here is particularly an edge filter. So it helps us to capture the edge information in an image. There are several other established filters that can be used as well. But also filters, as you will see, are also parameters that are learned by the convolutional neural network. So you wouldn't have to specify what filters needs to be applied. It is inherently learned by these algorithms. Yeah, so that said, in the future slides, I'll also show you how these outputs look when you have more than one filter, and also how these outputs look when we actually bring in the other two channels as well. That said, we're going to move on to another option that we have within convolution. So let's move on to strided convolution. So during the process of convolution, you can see how, in the previous slide, we saw how the input image was 5 cross 5, and then your output filter map was 3 cross 3, right? So what you saw over there is that it's the output is actually transformed into a smaller array while still maintaining the spatial correlation between the pixels by applying the filters, right? Here we'll also discuss how to compress the size of the input array much more, right? So we still want to be able to downsize this original image, but at the same time still maintain the information that's critical for us from the input image. So previously we saw how a 3 cross 3 filter was applied to this input image. So you saw how the filter was slided over by one column each time. So this, in the second pass we shifted it by another column until this column, and then the third pass we started from this column and it went on till the end. And then we moved down by a row, and then and then further down by a row. So we saw how we kept sliding or striding these filters over the input image, one column at a time until the end, and then one row down, and repeating the process. Um, so in this case, the stride was 1. So you could alternatively increase your stride rate, which is, for example, if my stride rate were 2, you'll see how you're going to be skipping a column when you move the filter over to the next column. So you see how um, you get the original 2 that was in the previous image, but now you're not taking this column as the beginning, but instead you're like skipping by 2 steps and then going on to the second column from where you previously started. And then when you move down a row, you're not moving down by 1 row, but instead moving down by 2 rows. So that's if your stride is 2. So why do we do this? Like I said, it helps us to compress our images further down, and also at the same time you're not missing key information in your original image. And by applying stride 2 or stride 3, if you feel like your image has been compressed too small, which means you've not essentially captured a lot of, or you've somehow missed information that was in your original image, you could downsize the stride to back to maybe just 1, or if it were a 3, you could downsize it to 2, and then see if you're getting better inputs. And these are all the general hyperparameters that you'll be like tuning to make your designer convolutional neural network per se.
Now that we know the size of the input image, that's 5 cross 5, and we know the size of our filter, that is 3 cross 3. Let's look at what the size of our um, feature map would be when we strided it at the rate of 2. So we see that it's 2, so 2 cross 2. So, and we know that k, which is the stride rate, so k is equal to 2, and we know that n is equal to 5, m is equal to 3. So given this formula that we would be applying, it's n minus m, which is 5 minus 3 by 2 plus 1 times 5 minus 3 by 2 plus 1. So that is 5 minus 3 is 2, by 2 is 1. Let me just scribble that down. So 2 by 2 is 1, and 1 plus 1 is 2. So that's 2 cross 2. That's how we arrive at the 2 cross 2 that's mentioned over here. Next, we'll look at an option called padding.
Again, still within the realm of convolution. So how is padding applied to an input image, or what does padding help us achieve? So we saw how in the previous slide, we saw how when you keep stride as 2, your output feature map is of size 2 cross 2. And if you recall, when the stride was 1, your filter map was 3 cross 3. So two things that we saw happens when you stride your filters over your input image. One, it downsizes your input image, which is good to a certain extent, but also it could potentially downsize your original image too small to an extent that for like further convolutions and pooling, as you'll see, your inputs are going to be much smaller. You probably don't want your output image to be much smaller. And also the other thing, if you observe, when this 3 cross 3 matrix was applied over the input image, you see how this was calculated first, and then you see how when it was strided by 1, we moved on to this cell, and then the final time when you moved over here, it was applied over that cell. And then when it like slided over down a row, we then had applied over here, and then so on. So what I want you to notice is you see how the information in the center has way too many dots than the information in the corner, right? So what this shows us is we are focusing more on the features that are towards the center of the image, but ignoring a lot of information that are around the border of the image. So to avoid this, we introduce this concept of padding. So to recap, to ensure that the size of the feature map retains its original input size, and also to enable equal assessment of all the pixels, you add one or more layer of padding. So padding refers to the process of adding extra layers of zeros to the outer rows and columns of the input array. So the previous image shows, like, how one layer of padding is added to the input array before a filter is applied. So there's also another formula that you derive over here to understand what the output size would look like if you apply a padding of size p. So in this case, your padding was size 1, so which means you added one row and one column full of zeros. So your n from your previous um, slides is n equals 5, m equals 3, um, p equals 1. Yeah, and then here we are assuming that the slide is we're just striding at the rate of 1. So that said, your formula would be 5 plus 2 times p, which is still 2, minus 3 plus 1 times 5 plus 2 times 1 minus 3 plus 1, which is 5 plus 2, that's 7, minus 3, that's 4, plus 1, that's 5. So 5 times 5. So that's the size of your feature map that you see over here. And while you implement CNN, you'll see how there is a parameter that you fix for padding that says size has same. So which means that you want your CNN to calculate what number of amount of padding should be added to my input image, so that my after applying the filters, after I've convolved it, my output filter map is still the same size of my original image. So that's a very common way of declaring what your padding has to be. In this video, we discussed about what convolutions are, and we discussed two options that come with convolutions, that are padding and striding. In the next video, we'll continue to look at convolutions to understand how filters are applied over the RGB channel, because in this video, we just looked at how filters are applied to the blue channel. We'll also extend to see how convolutions are applied using multiple filters. After that part, we'll jump into a technique for subsampling that's called pooling, and then we'll also look at what flattening is and how it connects to ANN. See you in the next video. Thank you for watching.